I'd like to invite Barrett to the stage. Let's give a warm round of applause for Barrett Williams. He is the current VP at a stealth startup and also previous developer and technical marketing manager exec at Scale AI.
Cool, thanks so much. So I'm going to try and go through today's presentation without actually saying the phrase AI, because I don't think it actually means very much anymore. I don't know if that's a controversial opinion in this room. And instead, I'm going to talk about how large language models are limited in today's environment and where they can expand and improve in the future, and how we might get to that better future. So yeah, just to share a little bit of context, I'm Barrett Williams. I currently lead product at a stealth startup, so I won't be disclosing exactly what we're working on today, but I'm going to set up a little bit of the industry problem that we see. And just a little bit on my background. I started out in this industry about 10 years ago at NVIDIA. I worked on the Jetson platform for 3 years. Then I joined Google and launched products like TPU v3, the ML Perf benchmark with Chris Latner, and then Auto ML Vision with Fei-Fei Li. And then most recently, I spent 2 years at Scale working on Nucleus, a dataset management platform, and then Spellbook, a large language model fine-tuning platform. So today I'd like to posit that model size actually does matter, and I think this is something that's played out a bunch of times over the past several years. And this is an example of Party, a generative image model. And here you can see a text prompt at the bottom, a photo of a kangaroo wearing an orange hoodie and blue sunglasses in front of the Sydney Opera House, holding a sign that says, "Welcome, friends." And you can see from the smaller models on the left to the larger model on the right, you can see there's a much upgraded, enhanced version of clarity and fidelity in the model at right. And we believe that extends to text models as well. This is an example of nat.dev comparing various 70 billion to 7 billion parameter models. The responses are actually kind of shockingly different across vendors like OpenAI, Llama 70 billion on Replicate, as well as MPT. So what are some of the macro challenges for LLMs? I'd like to posit that model size is probably the first and the biggest, as I kind of just showed in the generative image example. We've seen really impressive work come out of NVIDIA and Microsoft with DeepSpeed, 560 billion parameter model spanning across a whole data center full of GPUs. There's also context length, and context length is really challenging because it turns out that memory usage increases exponentially for longer context. So if you really want to have a super long prompt, you're going to fill up your GPU's memory almost immediately. And then lastly, these two first aspects really inhibit the ability to serve lots of users per machine. So that means there are growth opportunities here. At first, we can expand model size. And how do we expand model size? Well, we need more memory per compute core. And then we can also expand context length. Again, that's memory limited, so we need more memory. And then simultaneous user count. So we can get a little bit creative and clever about how we serve simultaneous users with the same model. We don't need to reinvent the wheel every time we context switch the next user and serve the next token. So it turns out longer context length, at least according to popular demand in the Twitterverse, says that longer context length is super useful. And some of the arguments as to why. You could actually inject your entire code base into the LLM prompt and generate new code based on that, following things like internal style guidelines and calling existing internal libraries. There's also a legal use case where you might point your model at a huge corpus of case law on LexisNexis, for example. And today those use cases are a little bit challenged because these are the context lengths for a number of the current vendors and models. So OpenAI, when they launched GPT-4, I believe they had an 8K context length, and you could actually pay $1.5 million a year to have a 32K context length with no SLAs. Pretty incredible. Claude 2 made a bunch of waves recently. I believe they have 100K context length. And then Cohere actually modifies the context length based on the model size that you're using. Lastly, there's also Inflection's model, Pi, and I just tested it out today, and the most I could put in was 1,000 characters. If there's someone here who knows that Pi has a longer context length, please do let me know. So this is a super common micro challenge some of you who are practitioners in this room may have encountered. So it's an out-of-memory error. You're trying to load the model, and as soon as you insert your prompt, or even you're just loading the model into the GPU, you sort of exhaust the resources of your system. And it turns out this plays a little bit into GPU memory design. So for a lot of the enterprise systems that you all might be training and doing inference on, like A100 and H100 in the cloud, you're using HBM memory, which actually costs a heck of a lot. It's $16 a gigabyte. It's super high bandwidth, low capacity. And I actually worked at NVIDIA when we switched to HBM from other types of commodity memory. And the motive was really to handle computer vision models, which at the time would not exceed, let's say 4 or 8 gigs of memory. And it's still okay. It's probably pretty useful for generative image models. But for large language models, it really just can't hang. There's, of course, the option of DDR, which we see in the gaming space, and that's only $4 a gigabyte. There are other memory types. There's SRAM on the chip. You might be able to load your KV or key value cache into SRAM on the chip or into NVMe storage to accelerate inference. There's also software advances. So this is flash attention. This is probably like the first significant performance improvement on Llama. And this came out of Stanford University. And it really addresses the fact that there are different tiers, different speeds of memory in the system to load the weights into. More recently, just about a week ago, page attention from Berkeley came out. It's at the VLLM repo. And here we see massive token rate speedups based on, so the left bar is a Llama 7 billion model on Hugging Face, and then you can see there's over a 10x speedup with VLLM. Another approach for improving performance is quantization. So if you've seen demos of any of these models running on a cell phone or something, you can actually take what is sort of a large data type. Let's say it's a number that is encoded into 16 bits. You can basically abbreviate that or shorten it or compress it into 1 or 2 bits even. These are some of the different data types that are common in the industry to compress the weights into. But we think there should also be hardware improvements. So today this is pretty much NVIDIA's architecture. Their on-chip memory is not designed really to handle KV caches or large language models. It's basically a most recent lookup from the HBM that's used. And basically when you tap out the memory size on your GPU, you basically have to ship the data back and forth across something called NVLink, which goes into the rest of your data center. And this is in what's known as a fat tree topology. So it's sort of not a very intentionally designed system, at least for large language models. So another approach you could take, and it remains to be seen who will build this out in the industry, but with increasing model sizes as you exhaust your SRAM and your HBM, you could hypothetically overflow into other types of memory like DIMMs or NVMe storage. And what's really cool about this is if you look at the old models on the left, like BERT and ResNet, they're really ideal for these lower high bandwidth memory capacities. Whereas if you keep going to the right, you're just going to exhaust the resources of your GPUs. So what ends up happening today, let's say you have an 8 GPU cluster, you're using all of the compute from the first GPU, and the remaining 7 are basically just used for their memory capacity. So we believe that future architectures should be able to address the fact that pretty much every GPU is constantly memory stressed. I'm going to switch now a little bit to talk about what this looks like in the context of the broader AI training stack. So at the bottom we have the hardware vendors, and at the top we have some of the major cloud providers. In the middle we have the model providers. So Meta just launched Llama V2 earlier this week. But of course there are proprietary and open source vendors in that list. And what's cool about the big box stack is we're actually seeing expansion into some second tier players like IBM and Oracle, just because the industry and folks like OpenAI just can't get enough GPUs. But what we really care about is the specialist stack. So there are smaller cloud service providers that really focus on ML, and they have dedicated teams to support these workloads. And everybody should be able to use what hardware they have to do inference and training. And I put Apple in parentheses because it looks like llama.cpp is now capable of running on M1 and M2 silicon, which of course you can't find in the data center, but at least you can run these models on your home dev machine. And then the question becomes, what's next? And so one hypothetical answer to this question is something that George Hotz is working on, TinyCorp. So his goal is to basically rewrite the entire ML stack to run on AMD, which is a more challenging prospect than it sounds. And I don't know, there's been a lot of debate in the Twitterverse back and forth as to whether this is feasible or not. But in the meantime, I'd like to just promote some of our friends in this industry. including Lambda, which we believe is a great hourly compute GPU provider. I spent a lot of today on Hugging Face downloading models from Tom Jobin's repo to run on local hardware. Yeah, so we believe there are huge opportunities in the ML hardware space to come, and stay tuned. Happy to take questions if anybody has any.
I love this presentation. Thanks so much for coming out and talking to us today. So I have a question that's kind of related to one of your first slides where you had that prompt for the generative image of the kangaroo holding that sign that said, XYZ words. I've played around a little bit with generative image models, and I'm curious why it is that, the higher the, token count or, the parameter count, the easier it is for words to show up on like the signs, because the ones like the consumer models that I play around with, it's like impossible to get to actually generate words in images.
Yeah, I think it's actually a matter of the size of the training samples that the algorithm learns on. So if they're not big enough, they can't actually include very much text, because a lot of times the text in the training data is so small, it's like nearly invisible. Whereas I think if you're trained on higher resolution images and probably more of them, so a larger data set, you'll probably get more robustness, especially if you encode it into more parameters.
Thank you.
Any other questions from the crowd?
Hi. I'm wondering what are your thoughts on distributed inference using solutions like, say, DeepSpeed or Pippi from PyTorch, or even a solution like Petals?
Yeah, I think distributed inference is great, but it's generally limited by the bandwidth interconnect within the system. And I think that's like a big reason that NVIDIA bought Mellanox to kind of expand out their high bandwidth interconnects within the data center. But if your topology is wrong, then it kind of doesn't matter. You're still going to be sort of bandwidth limited by the slowest point.
On a related thread, in data centers, are they considering optical interconnects for bringing in additional external memory?
Yeah, I mean, there are companies out there like Lightmatter, I think, that are doing optical interconnects. I don't know in terms of bandwidth, like what advantages that would provide you today. I don't know, maybe we could speak afterwards and you could share your experience on the matter.
All righty. Thank you, everyone. Thank you. Let's give a warm round of applause to Barrett Williams.
Thanks, everyone.